Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today, we are taking a really deep dive into the actual engineering behind controlling our indoor environments. We're going way past just fiddling with a thermostat. We're talking system architecture, thermodynamics, the real physics needed to keep a modern building comfortable all year long, no matter what's happening outside.
That's exactly right. And today we're drawing on some core engineering fundamentals, design practices from pretty technical guidelines on indoor environmental control. We'll focus mostly on central HVAC systems, how you select the key components, and that really complex job of air distribution, duct design.
Okay, and before we jump into the deep end, here's our goal for you today. Stick with us. And we're going to unpack, maybe, the biggest secret in HVAC efficiency. We'll show you why making a variable air volume fan, a VAV system, run at half speed doesn't just cut power use in half. Oh, no. It absolutely tanks it, drastically reduces it. And that leads to, well, astonishing savings in operating costs for big buildings.
hmm It's a fundamental engineering trade-off that, honestly, it changed commercial design.
All right, let's start unpacking this right at the core, the absolute heart of the operation. The central system. Doesn't matter if it's built-up equipment, constructed piece by piece on site, or big sub-assembled units shipped in. This is the engine room for year-round conditioning.
Yeah, the engine room. Good analogy. We're talking everything. The boiler for heat, the chiller for cooling, all the pumps, the piping, and crucially, the air handling components. Those are the bits that actually touch the air going into the space.
Right. And I guess the first big decision engineers face is how that conditioned air actually gets delivered.
Exactly. And today we're focusing on what are called all-air systems. That just means the system uses only air movement to handle both the sensible part, the temperature change, and the latent part, which is moisture control.
And the type of system you choose dictates how much control you get in different areas or zones.
Absolutely. The simplest setup is usually a single-path system. These are pretty basic. All the air gets conditioned to one single temperature, and then that same air goes through common ducts to every single area.
Okay, so cheap, but maybe not ideal. If I have an office facing the sun and one facing north.
They both get the exact same air temperature, yeah, which can be limiting.
Right. Seems very limiting for complex places like, I don't know, a hospital or a university building where the heating and cooling needs are just all over the map.
Correct.
So that must be where the dual path systems come into play.
You got it. Dual path is for hyper-precise temperature delivery. You actually maintain two completely separate air streams in ducts, one cold, one warm, and then these streams get mixed either right at the end, just before the air enters the room, that's a true dual duct system, or sometimes they're blended centrally, back at the main fan unit.
Ah, okay. More complex, but you get that fine control.
Exactly. The complexity pays off because you can satisfy, a freezing corner lecture hall and an overheating server room down the hall at the same time.
Okay, now let's talk about something that sounds, well, frankly nuts on the surface. The reheat system. Are you telling me engineers actually design systems that chill air down maybe to like 13 degrees C, essentially, only to then use more energy locally to heat it back up to maybe 18 degrees C? That just sounds incredibly wasteful. Why?
It does sound like a thermodynamic crime, doesn't it? But reheat is sometimes necessary. It's used when you need absolutely tight control over both temperature and humidity in a space, or maybe for perimeter zones that get wildly different sun exposure. So you often have to cool the air quite a bit just to wring the moisture out. That's the latent cooling part. And if doing that makes the space too cold, well, you have to add some sensible heat back in to keep people comfortable.
Ah, okay. So the main goal there is humidity control first, and then you fix the temperature afterward if you overshot.
That's the idea. And to try and claw back some of that massive energy penalty, good designs absolutely must use something called reset control. This basically tells the system to keep the cold air coil running at the absolute warmest temperature it can while still meeting the cooling and dehumidification needs. It minimizes how much reheating you have to do later.
Okay, so reheat is the sort of necessary evil in some cases. Then the modern hero must be the variable air volume system, VAV.
Absolutely. VAV is just brilliant. It handles varying loads not by messing with temperature directly, like reheat does, but simply by changing the volume of air supplied through a single duct. Room gets too warm, open the damper, give it more cool air. Room's getting chilly, throttle that airflow way back.
So each outlet, each diffuser, basically becomes its own little controllable zone.
Pretty much, yeah.
Which means lower initial costs, right? Fewer ducts, simpler controls maybe.
Generally, yes. Single duct ones are cheaper.
And the big one, the lowest operating costs of pretty much any all-air system, especially in big buildings where one side is hot and the other's cold.
That's the key advantage, especially with load diversity. And VAV tech has gotten really good. Modern systems can throttle the air volume way down, sometimes as low as 10% of the maximum design flow.
10%, wow.
Yeah, which makes it practical even for those tricky perimeter areas with huge swings in cooling needs. We should add, though, VAV is primarily a cooling system at heart. It really shines in buildings with big internal loads, think offices, data centers, places like that.
Okay, we've got the basic architectures, the what. Let's switch gears to the how much. If VAV is all about varying air volume, how does an engineer figure out the maximum volume they need to plan for? Let's maybe start with smaller systems, light commercial cooling, stuff under, say, 10 tons or 35 kilowatts.
Okay. Yeah, for that kind of typical light commercial packaged unit, when you look at the manufacturer's data, you'll usually see a coil sensible heat factor, the SHF. It's typically around, 0.75 to maybe zero point 0.8.
Sensible heat factor, SHF. Okay, what does that tell us?
It's a critical number. It tells you what fraction of the unit's total cooling power is actually going towards lowering the air temperature. That's the sensible part. The rest is going towards removing moisture, the latent part.
So an SHF of zero point 0.8 means 80% of the cooling energy drops the temperature, 20% pulls out humidity.
Exactly. And getting that balance right is crucial for comfort. People feel sticky if the latent load isn't handled, even if the temperature is okay. Now, for just rough sizing, getting a ballpark air quantity for this kind of equipment, there's a common rule of thumb engineers use. The air quantity needed is typically about 400 CFN per ton of cooling.
400 cubic feet per minute per ton.
Or in SI units, that's about 0.0537 cubic meters per second per kilowatt of cooling. You use that to get your total airflow, and then you divide that total amount among the different rooms based on how much cooling each specific room actually needs.
Okay, that sounds reasonably straightforward for a basic calculation, like a snapshot in time. But you mentioned earlier that figuring out the real energy use over a whole year is actually way more complicated than just that rule of thumb. What makes it so tricky?
It's the building itself. The biggest complicating factor by far is the thermal energy storage in the building structure. Think about it, the heavy concrete floors, the thick walls, even the furniture inside. They all soak up heat during the day like a giant thermal battery.
And then they release it later.
Exactly, they release it slowly, hours later.
So the sun might be strongest outside at, say, 2 p.m. hitting the walls. But the actual peak cooling load the HVAC system feels might not happen until 5 p.m. or even later, as all that stored heat bleeds back out into the space.
Precisely. You get this time lag, and the peak load the system sees can be quite different from the peak instantaneous load calculated from just weather and internal gains. So to get a truly reliable estimate of how much energy the building will use over a year, you really need complex, hour-by-hour computer simulations. These use typical weather data for the location and model how the building mass absorbs and releases heat. Simple hand calculations, like for houses, are really just adapted using average compressor runtime data from studies. You absolutely have to account for that building inertia.
Got it. That thermal mass changes everything for accurate energy prediction. Okay, so the building mass determines the load, but the fans are the muscles doing the work to meet that load. Let's talk about the air movers themselves.
Right. The main workhorse, the one you see most often in HVAC, is the centrifugal fan. It's incredibly versatile. It can move small or huge amounts of air, and it can work against low or very high pressures, which makes it great for complex duct systems.
Okay, centrifugal. What's the alternative?
Then you have axial flow fans. Think vanaxial or tubaxial types. They look more like a propeller in a tube. These guys move massive volumes of air, but they generally can't push against high pressures as well, and they tend to be noisier.
Okay, different tools for different jobs. Now, when we talk about turning electricity into moving air, efficiency is key. How do we measure fan efficiency?
There are two main ways. The most common one in standard U.S. practice is total fan efficiency, which we write as eta sub T. Conceptually, it's just a ratio. How much useful air power did we get out compared to the electrical power we put into the fan motor shaft?
And there's an equation for that.
Yep. The standard form is eta sub T equals Q times the change in total pressure, which is P sub T1 minus P sub T2, all divided by 6,350 times the shaft power, W sub Gish. Basically, flow rate times pressure change divided by input power with a conversion constant.
Okay, so that lets you check if the fan is performing as advertised. And you mentioned a second efficiency.
Right. There's also static fan efficiency, eta subsets. It's calculated almost the same way, but it uses the change in static pressure instead of total pressure. A slightly different perspective on performance.
Got it. Okay, now for the really cool part. This is where the VAV magic happens. Let's talk fan laws. These are fundamental, right?
Absolutely fundamental. These govern how fans behave when you change their speed. There are three main laws that are incredibly useful. One, capacity, the volume of air moved. Your CFM, or cubic meters per second, is directly proportional to the fan speed. Speed goes up 10%, flow goes up 10%. Simple.
The linear relationship makes sense.
Two, the pressure the fan develops is proportional to the square of the fan speed. Speed goes up 10%, pressure goes up 21%. That's 1.1 squared.
Square law for pressure. Okay.
And three, this is the big one, the power needed to drive the fan is proportional to the cube of the fan speed.
The cube, right? So if you double the fan
You
speed,
need 8 times the power. 2 cubed.
and conversely, if you cut the fan speed in half, like a VAV system does when the load drops,
You don't use half the power. You use 1/2 cubed of the power.
which is 1/8, you only use 12.5% the original power.
Precisely. That cubic relationship is the absolute game changer for VAV energy savings.
Wow. So even though putting in the variable speed drives the VFDs or magnetic couplings costs more up front.
The drastically lower power consumption over the building's life just blows away that initial cost. That single piece of physics is why VAV dominates large commercial buildings from an operating cost perspective. It's just huge savings.
Amazing. Physics paying the bills.
You could say that. Now, shifting from the powerhouse, the fan room, let's think about the delivery network, the ducts. Ultimately, the goal of all this ductwork, the air distribution system, is to create the right mixed temperature, humidity, air movement right there in the occupied space where people actually are. We need to achieve what we call acceptable thermal comfort.
And just like energy is lost in wires, energy is lost in ducts due to friction.
Right.
There's physics governing that too.
Oh, absolutely. We use the total head relationship to understand it. The detailed equation is complex, but the core idea is simple.
Okay, give us the concept.
The total pressure of the air, let's call it P sub O, always decreases as the air flows down the duct. So if you measure it at point 1, P sub O1, and then downstream at point 2, P sub O2, P sub O1 will always be higher. The difference is the energy lost to friction, what we call lost head, often written as I sub F.
So mathematically, something like P sub O1 divided by density rho, ignoring the G sub C factor for simplicity here, equals P sub O2 divided by rho plus that lost head term, I sub F.
Essentially, yes. P sub O1 over rho equals P sub O2 over rho plus I sub F. Total pressure drops because of friction loss. And engineers spend a lot of time trying to minimize that I sub F because every bit of pressure the fan has to generate to overcome that loss costs energy, costs money.
Makes sense. And one way to minimize loss is choosing the duct shape, right? You often see rectangular ducts because they fit nicely above ceilings, but circles are better aerodynamically.
That's correct. For the same cross-sectional area carrying the same amount of air, a rectangular duct will always have more friction loss than a perfectly round duct. It's just physics more surface area for the air to drag against, relatively speaking.
So how do designers account for that when they're sizing rectangular ducts?
They use a concept called the equivalent diameter, usually written as D sub E. There's a specific formula for it. D sub E equals 1.3 times, open parenthesis A times B, close parenthesis, raised to the power of 5/8, all divided by, open parenthesis A plus B, close parenthesis, raised to the power of 1/4, where A and B are the side lengths of the rectangle.
Okay, a bit complex, but the point is...
The point is it lets you calculate a circular duct diameter that would have the exact same friction loss per foot as your rectangular duct. So you can then use standard friction loss charts or software designed for circular ducts, even when you're actually installing rectangular ones. It standardizes the calculation.
Clever. Okay, so once you know how to calculate friction, how do you actually lay out the whole duct system? What are the main design methods, maybe for standard low-velocity systems first?
There are two main traditional approaches. The first is the equal friction method. It's pretty much what it sounds like. You design the system so that the pressure loss per foot of duct is the same everywhere for the main ducts on all the branches.
Okay, sounds equal. Simple.
It's relatively simple to calculate, yes. That's its main advantage. But the downside is that the duct runs going to the nearest rooms will have very little total pressure loss compared to the runs going to the farthest rooms.
So you end up needing to choke down the airflow to the closer rooms with dampers.
Exactly. You often need significant dampering on the shorter runs to balance the airflow, and those dampers can be noisy if you have to close them down a lot. That's a major comfort issue.
Right, nobody wants a hissing diffuser overhead. So equal friction is maybe easy for the designer, but potentially annoying for the occupant. What's the alternative?
The alternative is often called the balanced capacity method, sometimes static regain, though that's more specific. The goal here is much more sophisticated. You try to size the ducts such that the total pressure loss from the fan to every single air outlet is naturally equal or very close to equal.
So ideally, you wouldn't need much dampering at all.
That's the goal. It should theoretically self-balance the airflow to each outlet based purely on the duct sizing. It's much more accurate in terms of delivering the intended airflow and usually results in a quieter system. But it's significantly more complex to design. It takes more calculation time, more iteration.
Okay, trade-offs, as always. Now, what about those situations where space is just incredibly tight, like cramming ducts into the ceiling of a high-rise building where every inch costs money?
Right. When space is really at a premium, maybe due to high construction costs or just architectural constraints, designers often shift to high-velocity systems. Instead of large ducts with air moving slowly, you use smaller ducts with air moving much faster.
Which means you need more pressure from the fan to overcome the higher friction.
A lot more pressure, yes. You might see friction rates up to, say, 0.7 inches of water gauge per 100 feet of duct, which is quite high.
But you can't just blast air into a room at that speed and pressure. It'd be like a hurricane.
Exactly. So high-velocity systems rely heavily on specialized terminal boxes located near the actual room or space. These boxes are crucial. They take that high-pressure, high-velocity air from the small duct, they throttle it down to reduce the pressure and velocity. They often have controls to regulate the flow volume, like a VAV box, and, very importantly, they contain sound-attenuating materials to reduce the noise before the air finally enters the occupied space through a diffuser.
So the terminal box is like a combination pressure reducer, flow controller, and muffler, all in one unit near the room.
That's a pretty good description, yeah. Okay, let's pull this all back together. We've gone through systems, sizing, fans, ducts, but the whole point, the entire goal of all this intricate mechanical engineering is ultimately about the people in the building. It's about human comfort.
Right. Comfort isn't just temperature, is it?
Not at all. It's a complex mix. It involves the air temperature, yes, but also the radiant temperature from surfaces around you, the humidity level, and how much the air is moving. Get any of those wrong, and people feel uncomfortable. We actually have a standard for this, ASHRA Standard 55, which tries to define the conditions under which at least 80% of occupants will find the environment thermally acceptable. That's kind of the benchmark.
80%. So you can't please everyone, but that's the target. And besides comfort, there's the health aspect, the actual air quality.
Yeah.
You have to bring in fresh air.
Oh,
Yeah.
absolutely non-negotiable. You need minimum outdoor air ventilation rates, primarily to dilute the carbon dioxide that people breathe out, but also other indoor pollutants. The baseline minimum is generally never less than 15 CFM, that's cubic feet per minute, or about 7.5 liters per second, of fresh outdoor air per person. That's a fundamental safety requirement.
And thinking bigger picture, this ties into environmental control generally, doesn't it? The HVAC system isn't just doing temperature, it's often acting as an air cleaner too.
It really is, especially when you consider outdoor air quality. Many specialized air handling systems are designed specifically to deal with, or at least mitigate, common outdoor air pollutants, things classified as criteria pollutants. We're talking carbon monoxide, nitrogen dioxide, sulfur dioxide, ozone, and especially particulate matter, PM 2.5 and PM 10. The filtration choices, the air exchange rates, maintaining building pressure, these are all critical for protecting occupants from what might be outside.
So the mechanical system becomes a key part of the building's defense against pollution. Fascinating overlap. Okay, that brings us to our final provocative thought for you, our listeners, to chew on. We just spent time on how that cubic relationship in the fan laws makes VAV systems incredibly energy efficient over their lifetime because cutting speed saves so much power. So given that massive long-term savings potential, why might a design team still sometimes choose a slightly noisier, maybe less efficient constant volume fan like a simple centrifugal fan? If doing so significantly simplifies the ductwork layout, maybe uses less material initially, lowers the first cost of the project, think about that inherent engineering tension. The trade-off between spending less money up front versus saving much more money over decades of operation? Where do you draw the line?
Until the next equation, design junkies, we are mechanical engineering made simple.